Hello, my name is Miguel, and today I will teach you a little bit about X-rays and how they can be generated. If you ever had a broken bone or read a Superman comic, you know some of the uses of X-rays. However, this kind of radiation has a wide range of applications. In fact, ever since their discovery in 1895 by German scientist Wilhelm Röntgen, X-rays have found their place in a vast number of fields. From homeland security to painting authentication, these electromagnetic waves are very useful due to their non-destructive imaging capabilities. This happens because X-rays fall into the high-frequency part of the electromagnetic spectrum, with much smaller wavelengths than visible light. And we all know that high frequency means high energy. And it's this high energy that allows these waves to pass through materials that regular light can't pass through, making them perfect to image inside suitcases without opening them, for example. X-rays are also highly useful on academic research. Maybe the best example is crystallography, which is the field that experimentally determines how atoms arrange themselves in crystalline structures of minerals or biological molecules, like viruses. Other imaging techniques have also become highly popular in the past few years. Such is the case of X-ray phase contrast imaging, which is highly sensitive to variations in density, making it perfect for soft tissue imaging and real-time visualization of internal physiological mechanisms, like the respiratory system or the beating of a heart. However, these sort of applications usually require high-energy, ultra-short X-ray beams, available only at synchrotrons or free electron laser facilities, which are basically huge particle accelerators that cost up to hundreds of millions of dollars to build. These guys produce X-rays by accelerating charged particles, and then by making them oscillate using wigglers and undulators, in such a way that they generate radiation. The trick here is that accelerated charged particles actually emit radiation. This emission was modeled almost 100 years ago by these guys, Leonard and Vickert. This formula that you see here gives us the amount of radiation that an accelerated charge emits. You don't need to know much about it, but I'll tell you one thing or two. First, this bit here tells us that radiation is mostly emitted along the direction of the velocity of the particle. And this bit here tells us that more radiation is emitted when the acceleration is perpendicular to the velocity. This way, X-radiation may be generated by making a relativistic particle wiggle. And although nowadays this might be a very costly thing to do, plasma physics has come to the rescue, and luckily, efforts have been made to find an alternative high-energy X-ray source. Plasma-based particle accelerators are a compact alternative to conventional accelerators that use this thing called laser wake-field acceleration to bring the electrons to relativistic speeds. The idea is to combine these accelerators with some sort of wiggling system that would make the charged particles radiate, while making use of the high-intensity fields that usually appear in plasmas. In case you don't know what a plasma is, you can think of it as the fourth state of matter, a gas that has been given so much energy that its atoms break apart into electrons and ions. In this medium, with freely moving charges, wonderful stuff can happen. And my work is to model and simulate how charged particles emit radiation in extreme plasma conditions, using this equation that you might remember from before. In the end, I will hopefully have created a tool that allows us to understand how plasmas emit radiation, which may be a great help when designing the next generation of X-ray sources. But wait, there's more. Since most of the information we get about astrophysical phenomena is from radiation, this tool can also be of great help to understand phenomena that happened a long time ago in galaxies far, far away.